This program is brought to you by the University of California, Davis on iTunes U. For more information, please visit us at itunes.ucdavis.edu.
Splines, cubic splines, are the topic of tonight's lecture. And I think some of you had questions about the particular linear system solver that you need to implement for this assignment. Actually, I handed you on a one-page sheet at the very beginning of class a summary of the algorithm to deal with tridiagonal systems. Actually, it's just a loop, okay? You just have to write two loops to come up with a solution for that. So anyway, if you don't find that anymore, take one. Also want to say that this coming Friday, there will be a discussion section. Okay, Friday the, 12th, 14th? Friday the 14th. Is it the 14th or 15th, right? Friday the 15th, there will be a discussion section concerning B-splines, actually. So B-splines will be the next topic that everything will be focusing on in the coming lectures. So let's summarize. Where are we? We are at the point where we worry about constructing splines which are continuous in the sense of sharing a position, sharing a derivative, and also sharing second derivative, and where we want to represent the segments of the spline using our Bezier representations, our cubic Bezier representations. So just to reflect, in this setting, we use the idea of having these additional segments of a control polygon defining two interior Bezier points of a particular curve segment from a point pi going to a point pi plus 1. So this is one segment of the larger spline. One segment of a larger spline is defined over a part of the u-line, and so this particular chunk of the u-line would be from ui to ui plus 1, and I call the length here delta I. So then there are two neighboring intervals. This would be of length delta I minus 1, and this would be of length delta I plus 1. So we want to construct the curve segment from ui to ui plus 1, which should result in the segment going from a user-specified point pi to the next point pi plus 1. So the corresponding control points, these squares, then are indexed accordingly. So this would be point di, and this would be point di plus 1. So these given points are automatically part of the Bezier point sequence, and this one will be indexed B3i, and this one would be called B3i plus 3. Okay, and so we are after these two interior Bezier points. We need to know this guy, which is B3i plus 1, and we need to know this guy, B3i plus 2. And they will lie on this particular line, which will be split in a certain ratio. And the ratio for these segments will be given by these corresponding deltas on the u-line. So we will have a delta split here, delta I minus 1 to delta I plus 1. And this configuration will apply all over the entire cubic spline curve. So our unknowns that we are solving for in this system that we are setting up, in the system we solve for the unknown d's, di plus 1, and so forth, but ultimately we would like to find the Bezier points for each segment. The endpoints are clear, they are the given points, and the two interior points are certain combinations of the d's. So if I just write this down, what they are, then I can say from looking at the figure, I see B3i plus 1 equals is a combination of di plus something times di plus 1. What is it? I have to divide by the entire length, and that is delta I minus 1 plus delta I plus delta I plus 1. Here the same, delta I minus 1 plus delta I plus delta I plus 1. And then first point, the left d gets multiplied by the right length, which is delta I plus delta I plus 1. And the right d point gets multiplied by this length, delta I minus 1. Delta I minus 1. So that's this particular interior Bezier point. The other one, B3I plus 2, will be defined similarly as a combination of di and di plus 1. And so again, we have to divide by the same expression, di minus 1 plus di plus delta I plus 1, delta I minus 1 plus delta I plus 1. And then we are after this point. So this point now is this length times the di. So it's delta I plus 1 here, delta I plus 1. And this length as weight for the right d point. So that's delta I minus 1 plus delta I. So again, you have to do these computations for each segment of the overall spline curve, which goes on and goes on and goes on. The equation that's on the board, you don't have to copy it. You have it in your notes from last time, okay? This is the governing equation that relates the specified points, the p's, pi, with the unknown d points. Okay, there are 3 d points that are related in this fashion, defining one particular row or one particular entry for a set of linear equations. And I already talked about the end conditions last time, that there are certain degrees of freedom that we have to deal with at the endpoints of the curve. And I would like to make this more precise and just talk about that. So this is the problem. I want to talk about 3 types of end conditions. First, there are 2 types of curves. The first type of curve is an open curve, 2 endpoints. An open curve I want to construct. I specify a point, a bunch of more other points, and then the last point. I start here, I go over there. It's an open curve. And the other curve type, of course, is a closed curve, okay, a periodic, cyclic curve. That's the other type. So first we have to differentiate among the end conditions when we talk about them in the context of an open curve versus a periodic curve. Then, when we are dealing with the open curve case, we have to differentiate again between 2 cases. Case number 1 deals with the issue of the user specifying vectors at the end. There are 2 degrees of freedom, right? I said in the open case, there are 2 degrees of freedom. And typically, the user specifies the 2 end vectors at point 0 and point n. Or the user says, I would like to have what is called a so-called natural spline. A natural spline would be a spline that would, if extended beyond P0 and beyond Pn, continue as a straight line. Okay, that means that the curvature at these endpoints has to be 0, which translates into the second derivative being 0 in our setting. So that's a natural spline. All right, so the problem is we are dealing with 2 types of settings. First, there is the open case. Okay. And the open case is, again, split into 2 subcases. One case is called the clamped end condition, where you specify the end derivative vectors, clamped. Okay. And the other case is called the natural spline. Natural spline. What does it mean? In the clamped case, the user would go ahead, specify a bunch of points, and at the end points, she would also specify the vector. Okay, so here, she would like the curve to go up, and at the end, she would like for the resulting curve to go down. So the resulting curve would look like this. Okay, that is the clamped case. And the natural case, well, nature will take care of it. The user would specify 4 points. And then the natural case, if you were to put an elastic, plastic-like string through there, or a wooden beam, then it would want to extend in a straight line beyond the last points. And if you make that an assumption or a requirement, then you would start out like a line, and this would be the result. Again, nature would want to try to minimize the internal bending energy and would want to extend this in a straight line fashion where you have zero curvature, 0 second derivatives at these endpoints. So it's a natural setting. So again, here the user would specify the two end vectors, and here the user wouldn't specify anything except the points. So here is my point 0, and I also specify my point 0 prime, okay? Here's my last point, point n, and here is a point n prime derivative at that point. And here I wouldn't specify it. I would just say that the second derivative here, so this is p0, this is pn, and when I'm dealing with this natural setting, what it effectively means, it means that I specify the second derivative, p0 prime prime, to be 0 there, okay? And the same at the other end. I say pn prime prime equals 0. So that is case number 1, the open case, or the open spline, whatever. And the other is, of course, the periodic or the closed case, closed or periodic or cyclic, periodic case or spline. So what does the user specify there? Well, the user will specify point 0, point 1, point 2, point 3, and that's it, with the understanding that after point 3 I would go back to point 0. Okay, so point 0 equals point 4. So if I do that, I specify point 0, I specify point 1, I specify point I. Here this would be point n minus 1, and then the last point implicitly defined is pn, which coincides or is equal to p0. So, and the periodicity constraint will make sure that we have no degrees of freedom left. By just specifying the points, all degrees of freedom are taken up, and the resulting curve would look like this, right? You don't have to specify derivatives, because implicitly you force, at this point, the curve to share the same point at the beginning and at the end, to share the same derivative and also to share the same curvature. Okay, so it's implicitly constrained. So these are 3 important cases to consider regarding what to do at the endpoints. Okay, open case specifying 2 vectors, open case requiring that the thing would continue in a straight line, or a periodic curve. And of course, the periodic case is very important as well. There are many, many other cases. Okay, I do not talk about. So there are other end conditions that you will find in the textbooks. So the important configuration that we have to understand, the geometry is the geometry at the junction of 2 cubic segments. And so what is this geometry? Let me put this on the board again. So we have this control polygon defined by these squares, and then we have these interior Bezier points to be constructed based on those squares. And here we have a connector, and here we have one of those original points, pi, I call it. I is the general index. And then the curve will go something like that in that direction and something like that in that direction. We don't care about what happens outside. And so the curve is defined over an interval, so we are only interested in the junction of this left and this right segment and what's going on there. So we have 2 segments, and point I corresponds to u sub I. So this is u sub I plus 1, this is u sub I plus 2, this then has to be u sub I minus 1, and this is ui minus 2. So then the respective length of these intervals are delta I plus 1, delta I minus 1, and delta I minus 2. So these are the two segments we are interested in, curve segment left and curve segment right. The left one mapping here, the right one mapping there. Point Pi belongs to or implies control point di, so this guy then is called di minus 1, and this guy has a name di plus 1. Pi will become Bezier point B3i, and so these are also Bezier points in their own right. This one then will be B3i plus 1, this is B3i plus 2. And then these guys will be B3i minus 1, and this is B3i minus 2. And I said before, everything in this geometrical illustration is based on the ratios given by these deltas, the length of the intervals on the u-line. Where are they? Where do they occur? Well, they map here. This also has to be delta I minus 1. This is delta I. And these three line segments will be split in this ratio, this to this to this, which is delta I minus 2 to delta I minus 1 to delta I. And these three line segments will split this entire line, given by the ratio of this length, and that length. So here we have delta I minus 1 to delta I to delta I plus 1. This language is the same. No, this is a different language, a different way to describe the same thing. This figure is captured in that formula, okay? These geometrical constraints ensuring that these two segments at this breakpoint come together in a smooth or C2 continuous fashion, these constraints translate into this figure, and this figure translates into this formula. It's the same. It's one and the same. So now, where's the linear system? I said that is, of course, a linear system where I runs from where to where. Our first point is called P0. Our last point is called Pn. So this equation holds for I from 0 to n. Right? So here, I is from 0 to n. But that isn't quite good enough, because if this is P0, there's this additional d point to the left, which is the degree of freedom. If this point is Pn, and this is dn, then there's this additional degree of freedom, dn plus 1 to the right. Those are the two degrees of freedom, and those relate to the end conditions. And now actually I have to drive towards the particular formulas that relate to these three types of end conditions: clamped, natural, and closed. So let's see how that goes. Okay. This is all the same, right? This is it's a linear system of equations. This is the geometry. And now I write it in matrix form. It's all the same. Now I write the same thing in matrix form. Matrix form. Okay, matrix form. There's this big matrix. And you solve for the unknown d points. And the d points go from d minus 1, d0, up to dn and dn plus 1. And on the right-hand side, you have something else. Also, in the spirit of simplifying that, last time I said I just call this expression alpha I. Okay, I call this expression beta I, and I call this coefficient here gamma I. And I said I call the sum of those two deltas omega I. Okay? So then this equation is nothing but alpha I di minus 1 plus beta I di plus gamma I times di plus 1 equals omega I times point I, right, in abbreviated form. And so you have to define these things as functions or procedures only once in your program, and that's it. And then you only think on the higher level in the summarized form like that. Now this is an entry in this matrix equation. So for the first d0 point, I just put it in there, means here I have alpha 0, beta 0, gamma 0. Okay? Equals on the right-hand side omega 0 times 0.0. Bam, bam, bam. And the last one here will be omega n times point n. And the last valid row here for I equals n, you plug it in there, what that means. That means alpha n, beta n, gamma n appears in that row, and they multiply dn minus 1, dn, and dn plus 1, and they lead to omega n times pn. Now, this is the tridiagonal matrix that I talked about. All the entries that are different from 0 occur only on the three main diagonals. This is 0, and this is 0. And now I already separated out the top and the bottom line in this matrix, in this equation system. Why? Because this first line corresponds to end condition number 1, end condition 1 on the left end. And that is condition 1, right? It's related to that, condition 1. And this is the second end condition. What I require the curve to be at the second end, at the endpoint Pn. So I call this end condition number 2. And so this is related to that condition 2. Condition 2. And so important part, we only have to deal with beautiful and simple tridiagonal matrices, which we can handle in linear time, right? So tridiagonal matrix, tridiagonal matrix. And you have in your handouts a very simple pseudocode how to compute the unknown d vector from this system. Now we have to go actually into the specific end conditions and talk about the different types: clamped, natural, and closed. Do we need this? No. So let's go into case number 1 first, right? Case number 1 has to deal with the fact I specify the points, clickety-click, and I specify 2 end vectors, right? And how does this specification of end vectors relate to the first and the last rows in this linear equation system? That's what we need to figure out. Let's just write it down, okay? we write down what the derivatives are formally of such a curve at the endpoint, and then we make requirements that these derivatives take on certain values, namely the values that the user specifies at the end. Okay. First, specifying derivative vectors, or just derivatives, first derivatives, at P0 and Pn. Okay, so that is case number 1, clamped end condition. Clamped end condition. Okay. We have to understand the situation. And so the situation, what does it look like at the left? Okay, at the left, at the beginning of the curve, the situation looks as follows. There's a square, there's another square, and a happy square to end with. And we want to know how this thing starts out. So here are these other Bezier points. Here is one, there is one. This is the first segment we are talking about. So this is point P0. And we would like the curve to have a certain derivative there. Now we know that the derivative is in line with this and that Bezier point. So the derivative would look somewhat like that, right? The derivative is specified, a vector, start out like that. So the curve should behave like that. And I call this P0 prime. Why not? P0 prime. Then what are these things called? This is called B0. This is called D0. This is called D1. And this is D minus 1. And at this degree of freedom that we are concerned about, how is this guy specified or implied by us specifying the point and the derivative there? Okay. So if this is B0, then this guy is called B0, B1, B2. So B0, this one must be B minus 1, right? Don't be shocked by that. It's a negative index, who cares? B minus 1. Okay, it's just a formal derivation of what's going on there. Here's my U line. How do I start out at the beginning? I start out like this. We are talking first segment. The first segment goes from U0 to U1. Right, this is the first segment for that curve. And then here are these two additional values to the left, U minus 1 and U minus 2. So the deltas involved here are these. This is delta I minus 2, or delta minus 2, minus 2. This is delta minus 1. And this is delta 0. Okay. All right. What else do I need? Now I need to write down what the derivative is at this point. What is the derivative at this point? The derivative is a curve evaluated at U0 prime. What is it? And we have to remember what the formula was for a Bezier curve. It is essentially last point minus previous Bezier point times 3 divided by the length of the interval. So that was 3 divided by, and don't be shocked that I use delta minus 1 times B0, which is P0 minus B minus 1. Okay. This is the derivative as it will come out when I later evaluate this line. And I want this to take on a certain value. I want this value to be P0 prime, the value that I specify. So this should be, by mandate of the user, P0 prime. I specify that, right? I want it to be P0 prime. That's the condition for specifying the derivative there. What is the unknown here? I have to solve for B minus 1, right? B minus 1 is the unknown because P0 is specified and P0 prime is specified. So I have to solve for B minus 1. Okay, so what's b minus 1? When I solve this for b minus 1, I get b minus 1 equals, and now do you see that? I multiply by delta minus 1, divide by 3, and then bring it on the other side. Huh? So do that in your head, right? Times, then you have P0, P0 minus, right? Minus delta minus 1 over 3 times P0 prime, okay? Solving it for b minus 1. What else? You have another equation for b minus 1. That's the equation that we like to think of in terms of the d's. So you can express b minus 1 in terms of d minus 1 and d0. That's what we need, because we need an equation system for the d's. Huh? So now we write down what b minus 1 is relative to d0 and d minus 1, again using these ratios. Where are those ratios? Those ratios pop up here. This is d minus 2, this is d minus 1, and here is d0. Okay, so we also have b minus 1 equals, okay, well now we do this combination business again. It's something times d minus 1 plus something times d0. And what's in front of it? Well, we have to divide, normalize by delta minus 2 plus delta minus 1 plus delta 0, delta minus 2 plus delta minus 1 plus delta 0, delta minus 2 plus delta minus 1 plus delta 0. And then we are talking this point, so left d gets multiplied by d0, delta 0. And right d point gets multiplied by that length. This is delta minus 2 plus delta minus 1. Okay, so now we have two expressions for that. Now we can equate it, okay? So the equation, so this is end condition 1, right, that we are after. End condition 1, then looks as follows. It is this expression equaling that one. Right? Two expressions we have for b minus 1, and we set them equal. So we have delta 0 over delta minus 2 plus delta minus 1 plus delta 0 times d minus 1 plus delta minus 2 plus delta minus 1 divided by delta minus 2 plus delta minus 1 plus delta 0 times d0 equals what we specify. We specify the point P0, and we specify point 0 prime, and I have to put a factor in front of it, and that is delta minus 1 over 3. So that is the additional end condition when I specify the derivative at the left end. Now, of course, I can do the same at the other end, or I have to do the same at the other end to get my corresponding second condition. And I put that here. The other end, how does the curve end? I just make a picture, and from the picture I can always derive everything. So how does the curve end? I put the picture here, why not? This is the way the curve ends. This is delta, this is dn, this is dn minus 1, and this is control point dn plus 1. So I have these Bezier points here. I have here the point that I want to interpolate. That is the last point. I call it Pn. And again, I specify also the derivative there, which would go in this direction then. This is the end point derivative, which I call Pn prime, user specified. So then this point Pn would be Bezier point B3n. So this point here would be B3n plus 1. And this point is B3n plus 2. what is the parameter interval there at the end? U. This is the last segment we are talking about, so it ends at un, right? Un is the last point Pn, and so this is un minus 1. Then this would be un plus 1, and this is un plus 2. So the corresponding distances or length are delta n minus 1, delta n, and delta n plus 1. Where do we find the ratios of these three? Well, we find them up here. This is a ratio delta n minus 1 to delta n to delta n plus 1 in that figure. And now we do the same game again. We write down what it means for requiring the specified derivative to come out. So we have the curve differentiated at the last parameter value u sub n is what? It has to be 3 times divided by, this is delta n, 3 divided by delta n, times a difference between this Bezier point and that Bezier point, b3n plus 1, b3n plus 1 minus pn. Okay, and again, the unknown is the b3n plus 1, but we want this to take on a certain value, namely the value pn prime, user specified. That's the condition. Okay, so we solve this for b3n plus 1. When I do that, I get b3n plus 1 equals what is it? Do you see that? Can someone help me what it is? I multiply by delta n divided by 3 and then collect terms. So what is it? This one remains, so that is what? Huh? It's Pn plus, right? Plus delta n over 3 times the derivative specified there, Pn prime. It's important to note that here we have the negative, okay? And there we have the positive at the other end. Okay, don't overlook that. And so now we also write down another expression for this B point, expressing it in terms of the last 2 D points, okay? So when we do that, we also see that b3n plus 1 equals, it is something times dn plus something times dn plus 1. And what are these factors in front of it? Well, we have to divide by the sum total of all these deltas. So that is delta n minus 1 plus delta n plus delta n plus 1. Same here, delta n minus 1 plus delta n plus delta n plus 1. And then we are talking this point, that point must be multiplied by that length, which is delta n plus delta n plus 1, means that dn plus 1 is to be multiplied by that length, delta n minus 1. Delta n minus 1. So that's the other expression for this Bezier point, and now we can set them equal. And by setting them equal, we have what we want, namely a linear equation for the 2 Ds. Okay, so end condition 2 follows. End condition 2. End condition 2 then reads dn plus dn plus 1 divided by delta n minus 1 plus delta n plus 1 times dn plus delta n minus 1 over delta n minus 1 plus delta n plus 1 times dn plus 1 equals, it has to be Pn plus delta n over 3 times Pn prime. So this is the second derivative at the other end. So we have two beautiful end conditions. End condition 1 and end condition 2. Now is the time to look at the special case. The special case is the spline when the u sub I values are just I, when you just use an integer-based parametrization. And then the matrices and all these ugly expressions which you should not and cannot remember, all these expressions become very simple and you can remember the matrix for that setting. So I just want to put this here. A specialized case, special case is when all u sub I values are I. Okay? U sub 0 equals 0, u sub 1 equals 1, and so forth. Integer. Then all these things simplify drastically, and the system of equations that you have to deal with looks very beautiful and simple. You can remember it. So the unknowns are d minus 1, d0, and so forth. And here we have dn and dn plus 1. And the entries, well, the interesting ones are the end condition entries. But all the other ones are 1, 4, 1 entries. 1, 4, 1. 1, 4, 1. And on the right-hand side, you will have 6 times this vector. And it will always be the points. There was a delta plus a delta, right, and so forth. So this is just point 1. This is point 0 here. And then the last one here is point n. Something goes into the first and the last rows. And the stuff that goes in there follows from evaluating these two equations by plugging all the delta i's being 1 in there, right? When I have a uniform spacing, all the deltas are 1. So what do you get? You get 1 over 3, 1/3, times something plus 1 over 2/3 times something equals this point minus 1/3 over times that derivative. Long story short answer, when you actually figure that out, you get the specific answer for that system. And I want to put this down, what these values are for the specific setting. And in the first row, it is P0 over 2, P0 divided by 2 minus P0 prime divided by 6. Okay, that is the first end condition. And again, important, here this is minus, and the end condition on the bottom, the last end point is P n divided by 2, and this is plus the derivative there, Pn prime divided by 6. Okay. And what do we have here? Here we have a 1, 2, and here we have 1, 2. So again, it's a beautiful tridiagonal matrix, and all the rest is 0. Okay. So this is the end condition at the beginning and the end, and the right-hand side for those two endpoints. So this is a case where we require the spline to have certain derivative vectors at the ends. And now comes the setting where I want the spline to behave naturally, meaning it should have 0 second derivative. So that is the next case. Are there any questions so far? Is it clear, pretty much? How I derive these things and how I go from the geometry to the algebra and to the system? Is clear? It is, right? And by the way, if something is not quite clear, look at the lecture again at home. And if it's still not clear then also look at the book, right? The book tells the story a little bit differently. Now, I want to point out that the book of Farrand, Gerald Farrand, deviates a little bit at this particular point from the way I derive this linear system. Okay, he uses what is called triple end knots. So, and I talk about that too. His linear system looks a little bit different. Mine is a general version, and his version is a more specialized form of that. Okay, so when you compare my entries for the elements of that matrix with his, they look slightly differently, but only for the end conditions at the beginning and at the end. Okay, but my case is a general case of his, so don't be confused because of that. So the next case is the natural case, natural end conditions. Natural end conditions. And this relates to what is called the natural spline. So when you just see the word or hear someone say natural spline, this is what they mean, okay? Natural spline. So this meaning spline must have 0 second derivative. I must have 0 as second derivative at the endpoints. Second derivative at endpoints P0 and Pn. So again, we have to investigate what that means for the curve to have a second derivative at the beginning that is 0. Okay, so again, I put the similar geometry on the board. This is D0, this is D1, this is D minus 1. I have my Bezier points here. Here I have my original point, P, that I specify, P0, which is also B0. My parameter interval for the beginning of the curve is here, U0, U1. Then I have 2 to the left, U minus 1 and U minus 2. And again, the degree of freedom that I'm always wrestling with is this point, D minus 1. I need an expression that linearly relates these points somehow. And now I'm looking at the second derivative at this point. What is it? And so this point then is Bezier point b minus 1, and this is Bezier point b minus 2. All right, what can I say? Also put my ratios here again. These ratios are delta minus 2, this is delta minus 1, this is delta 0. And I put those ratios here as always, delta minus 2 to delta minus 1 to delta 0. And now I have to remember what the expression was, or the formula, for the second derivative of a Bezier curve. Okay, so I have to write down what is the second derivative. Second derivative at p0. I write it down, and I call it c prime prime, right, or c dot dot, if you like that notation. C prime prime at the beginning at u0 is something. Okay. This is the part for which I will write it out. Do you remember what that was? The second derivative of Bezier curve? Maybe we should remind ourselves what that is. Right? For a cubic Bezier curve, you don't have to copy this, you have it in your notes. If I give you a cubic Bezier curve, which is defined over some interval from alpha to beta, and this has some length delta, and this is a b0, a b1, a b2, and a b3, then there is a curve, and this curve has a certain second derivative at the, right, at this point. Let's evaluate it here, for example. What is the derivative, second derivative there? What is c prime prime there at this location beta? What was it? Remember what that was? So that had to do with something like 3 factorial. You remember that? Huh? N minus r factorial over. Remember it? There was an expression here, and then there was something along the lines of times b3 minus 2 b2 plus b1, right? The factor will become irrelevant, and therefore I won't put it there. There is some term times an expression, a combination of 3 consecutive Bezier points. In this case, those would be p0 minus 2 b minus 1 plus b minus 2. And I say I want that derivative to be 0 at the end. So I set that expression to 0. I want this to be 0. So the condition for the natural spline to have 0 second derivative becomes 2 b minus 1 minus b2 equals p0, right? 2, I bring it on the other side, 2b minus 1 minus b2 equals p0. That's the condition that, if satisfied, implies a second derivative of 0. Okay. So now again, the Bezier points are not the ones we solve for directly. We solve for the d points. So now we have to express b minus 1 and b minus 2 again in terms of the d's, which we can always do. It's no problem, right? So we can now say, what is b minus 1? B minus 1 equals, what is b minus 1? We look at the figure. B minus 1 is something times d minus 1 plus something times d0. What is it? We have to divide by delta minus 2 plus delta This is delta minus 2 plus delta minus 1 plus delta 0. Here again, delta minus 2 plus delta minus 1 plus delta 0. And then this is b minus 1, so it is multiplying the left d minus 1 point by delta 0. And the other one has to be delta minus 2 plus delta minus 1. And we have b minus 2 being correspondingly a combination of d minus 1 plus something times d0. What is it? We have to divide again by delta minus 2 plus delta minus 1 plus delta 0, delta minus 2 plus delta minus 1 plus delta 0. And now we are talking b minus 2, so Bezier point b minus 2 has to have delta minus 1 plus delta 0 here. And here it has to have delta minus 2. Okay. So these are expressions for these two Bezier points which occur in the equation, and now we plug it in. Now we just plug the expression for b minus 1, b minus 2 in that equation, and we have the condition. Okay, so when we do that, so now we can go back to this one. We have 2b1 minus b2. We can just do this here by looking at what's on the board, right? 2 times this minus that. So 2 delta 0 minus delta 0 is delta. So this remains delta minus 1. This was 2 delta 0 minus delta 0. So this was also a minus delta minus 1 plus delta 0 over delta minus 2 plus delta minus 1 plus delta 0 times this control point, d minus 1. Was it correct? 2 times this, 2 delta 0 minus delta 0 gives delta 0 minus delta minus 1. There's a minus, okay? Plus something times d0. Again, it's 2 times b minus 1 minus b2, so 2 times this stuff. 2 times delta minus 2 minus delta minus 2 gives delta minus 2. And this 2 times plus 2 times delta minus 1. Okay, 2 times delta minus 1 divided by delta minus 2 plus delta minus 1 plus delta 0, which should be on the right-hand side, 0.0. That's the condition. That is end condition number 1. Okay, that's end condition number 1 for the natural spline. End condition 1. End condition number 1 is this. Now we do the corresponding for the other end. At the other end, we again look at the configuration first. How does the curve end? The curve ends like this. dn plus 1 and dn minus 1. And we have Bezier points. Here is the last point that the user specifies, Pn. And then the parameter interval looks like what? Here's my u-line. The last relevant interval ends here at un, so this is un minus 1. And we have 2 additional ones, un plus 1 and un plus 2. And here is delta n minus 1, here is delta n, and here is delta n plus 1. These ratios map onto the last segment. So here we have delta n minus 1, delta n, and here we have delta n plus 1. This last point is equal to b3n. So this point here is b3n plus 1, and this is b3n plus 2. Again, what do we require? We want the curve to end with a 0 second derivative. So there's a condition on these 3 points. So if we require that, what is the second derivative? Second derivative at Pn. Okay, again, so I call that the second derivative C prime prime at un is some term we don't care about times a second forward difference at Pn, which is Pn minus 2 b 3n plus 1 plus b 3n plus 2. Okay, and that, as a requirement, should be 0. Okay, that's the requirement, to be 0. This is the requirement here. This is the requirement. What are the unknowns in this equation? The unknowns are the two b's. So again, I write this differently by putting the point Pn on one side. So I have 2 b 3n plus 1 minus b 3n plus 2 equals Pn. And that is the condition at the right end. And again, I can spell this out in detail by saying what is b 3n plus 1 equals bam bam bam, and now I won't do it anymore. And I spell out what is b 3n plus 2 equals something. Ultimately, I will just plug these expressions for the b points into the equation to get my final equation. And I put it on the board what it is. The equation that I get is my second end condition. End condition 2 comes out of this. End condition 2, end cond 2, that will follow, looks like this. It looks like this. It's 2 delta n plus delta n plus 1 divided by the sum of these deltas, delta n minus 1 plus delta n plus 1 times dn plus, again, dividing by delta n minus 1 plus delta n plus 1. And here it has to be delta n minus 1 minus delta n times dn plus 1 equals, on the right-hand side, the point, the last point, Pn. So this is the second end condition at the other endpoint. These conditions look horrible and look very bad and complicated, and you will make all kinds of mistakes when you first implement it, because you will screw up somewhere with the index, right? You will be off by plus or minus 1 with the indices. It just happens. So I hope I didn't put too many wrong indices on the board. But anyway, when you do this at home, again, then you will see a certain pattern for all these indices emerge. What does this mean when all my spacing is uniform, when all my deltas are 1? Then this becomes trivial. When all my deltas are 1, then what does this read? How does this read? All the deltas are 1. What is this? Plug 1 in there for all the deltas. Minus 1 plus 1 is what? 0. So this is 0, right? What is this? 1 plus 2 is what? 3. And 1 plus 1 plus 1 is? It's 3 over 3 is 1. Right? So what is 1 times d0? It's d0. It's very simple. It becomes d0 equals p0. Okay? Same here. What happens for the special case when you have a uniform equidistant parameterization? Plug delta equals 1 in there. It's 2 plus 1 is 3 over 1 plus 1 plus 1. 3 over 3 is 1. 1 times dn plus 1 minus 1 is 0. So it's just 1 times dn. dn equals pn. Okay? So in the special case of a uniform equidistant parameterization, you have the end conditions read like this. Special case. Special case. Special case. The special case is u sub I equals I. you have end condition 1, end condition 1 reads D0 equals P0. That's it. Okay, and end condition 2 reads Dn Dn equals Pn. Okay. How does this impact the matrix? These are just entries, right? This is the last row of the matrix, and this is the first, and this is the last entry in my linear system of equations. Let's see how that looks like now. So you can easily start testing your implementation by just using the uniform equidistant parametrization first, when all these equations become simple and you have very simple numbers in your matrices. Right, so in matrix form, this becomes very simple now for the naturalist line. Here you have the main part. Here is the unknown vector, right? So it goes with d minus 1, d0. Last one is dn, and here is dn plus 1. The unknowns equals something times, there was a 6 in front of there, right? In front of that. If I remember that correctly, there was 6 times something. And then something. What was it? There was a bunch of 1s for 1s and 1 for 1 entries, right? That was it throughout. And then here it was just the points, point 0, and so forth, and point n. And now we have, for the special case, this one additional and this one additional equation to insert. So 1 times d0 equals p0, right? 1 times d0, 1 times d0, 1 times d0 equals p0. Okay, so a 6 goes here, right? 6 p0. Right? Here's a 0. Right? 0 times d minus 1 plus 6 times d0 equals 6 times p0. That is this, d0 equals p0. 0 times d minus 1 plus 6 times d0 equals 6 times p0. So it means d0 equals p0. Same at the other end. So here is 0, 6, and at this end it ends similarly. Here is 0, and here we have 6. Okay. So again, the rest is all a bunch of zeros. And you still have a nice, beautiful tridiagonal system. And here we have Pn again. The end conditions are these. Okay. So since there's not enough time left for me to talk about the next case, I will just give an outlook to it, okay? So what was the last case of dealing with end conditions? Closed, a closed curve. You don't have degrees of freedom. Everything is specified by requiring the curve to be closed. What is the simplest curve for the closed case? How many points do you need to specify to get a closed curve? The first meaningful closed curve, how many points do you have to specify? How many? Give me a number. 2? You can get a closed curve with 2? What would that look like? The closed case, right? Can I get a closed curve is 4? Do you believe me? Probably, right? So 0.0, 0.1, 0.3, 0.4, and the implicit understanding that 0.5 is 0.0 again. So that's modulo, right? Modulo 4, 5, right? So here this is 0.0, 0.1, 0.2, 0.3. We start counting at 0. We are C programmers, right? So it's modulo 4, right? Everything is modulo 4. Huh? N equals 4. Huh? So, and then the curve I get looks like that. Okay. Can I construct a closed curve with less than 4? Can I do it with 3? Can I do it with 3? 0.0, 0.1, 0.2, and 0.3 the same, right? Like where I started. So first cubic, second cubic, third cubic, right? Of course, I can do this too. So the first meaningful one is one with 3 or 4, right? How many points are here? 3 or 4? Well, when your number is really 0, 1, 2, 3, there are 4 points, but the last one is the same as the beginning, so it depends on how you view that, right? So 3 points, 3 distinct points is the first meaningful curve. Of course, you can also do one with 2, right? 1, 2, 1. Right? Of course, you can do the 2. 0, 1, 2. Back, right? The curve you get is, of course, there. Right? So, of course, I mean, you can do a closed curve with 0.0 and you stay on the point, right? With 1 point. Right? It's a closed curve, too. It's just, so these are kind of like the general cases, right? So this is the issue we talk about next time. And so how do we have to think about this closed stuff? The curve, this is the way it works, right? I have a first I'm thinking about just 3. The simplest case is 3 segments coming together, right, in this fashion. So I specify a first point, a second point, a third point, with the implicit understanding that the last point would be the first point again, okay, and then it's closed. Okay, so the curve segments are nothing but pieces on the line that are deformed. Huh? So I have 3 curve segments. That means there are 3 pieces on the line which will become that segment. So I have piece 1, I call it curve 1, I call it curve 2, I call it curve 3. So for 1, 2, 3, there must be 3 intervals, right? This becomes curve 1, this one becomes curve 2, and this one becomes curve 3. Right? That's the correspondence between these intervals and the deformed curves. And then what? But I also need these deltas. What happens now? You really have to think about this. This is wrapping around now. Huh? This is U0, right? U1, U2, U3, U0, U1, U2, U0, U1, U2, U3. But U3 is when you come back to U0 in a sense, right? It's going around in circles. So you really have to think about you travel along, and then somehow you come back to the beginning, right? That's a cyclic. There's a cyclic nature to that. So that means that these deltas, delta 0, delta 1, delta 2, continue. Delta 0, delta 1, delta 2. Okay? So this is delta 2, delta 1, delta 0, delta 2, delta 1, delta 0. So these deltas get cyclically repeated at the ends. So you can also say, okay, if I have a closed curve, then I also would like to have a closed parameter domain. Huh? So you can say, you start here, you start there, and you can have the parameter line could itself be a curved parameter, a space that is cyclic, right? Anyway, so next time we will talk more about how to construct a curve where you make sure that it's C2 continuous at all the breakpoints, and we worry about what that means for this delta stuff to wrap around. Thank you.
The preceding program was brought to you by UC Davis on iTunes U. Please visit us at itunes.ucdavis.edu.